Hi, this is week 28 of chemistry, and in this week we'll be looking at the first lesson of unit 6, which is chemical thermodynamics. For our agenda, we'll be looking at the difference between an endothermic reaction and exothermic reaction, as well as phase diagrams. For lesson objectives states that students will learn how to distinguish between endothermic and exothermic reactions, and students will be able to draw and use a phase diagram.
So let's get started. Let's begin with energy. Energy is the ability to do work or produce heat. Now, there's two types of energy. There's kinetic energy and potential energy. Now, let's get a little bit about what is kinetic versus potential energy. In the picture on the right, you can see Hoover Dam. Now, Hoover Dam has a lot of water behind the dam. Now, the water could do work. So the water that's behind the dam, you would refer to as having potential energy because it could do work. On the other hand, kinetic energy. Kinetic energy is the energy of an object in motion. All right, so in the example of the picture, once more time, you see that water shooting out. That's going to go ahead and spin turbines within the dam and create electricity. All right, so that water that is in motion has kinetic energy. Let's look at it a little bit more in depth. So kinetic energy is possessed by an object in motion. For example, on the top right, you see the picture of those athletes running across the finish line. They have kinetic energy because they are in motion. They're moving across the track. Also, the ice skater spinning also has kinetic energy, rotational kinetic energy. Even though she's standing in the same spot, she does have movements and she is rotating. Now, potential energy could be stored in different ways. All right, it could be by virtue of its position. For example, on the picture on the bottom left, you see the high diver. She is well above the surface of the water, so she has potential energy due to gravity. On the next picture, you see the athlete also pulling back on the bow and arrow, and that will create tension. So the stress within the bow, that has the potential to do work, which is push the arrow forward. So that's also another example of potential energy within the bow. And lastly, electric charge could be, or electric energy could be also potential energy. That battery could do work. All right, so those are the great examples of kinetic and potential energy. Let's go ahead and move forward. Now we're going to go ahead and look at what is an endothermic versus exothermic reaction. So it's a chemical reaction that absorbs energy is called an endothermic reaction. An excellent example of this would be in a first aid kit. You come across that instant cold pack, and all you do is mix it together, break it, twist it, and then what that will do also remove a barrier separating two chemicals together that will mix and it'll get cold. See that cold feeling? It's an endothermic reaction. It's removing the heat from everything around it and absorbing it, so everything around it feels cold because it's having its heat being removed. So it's an endothermic reaction, one that requires heat to proceed. On the other hand, an exothermic reaction is a reaction that releases energy. If you've ever been in a place where it gets really cold, they have hand warmers. They work very similar as the ice pack. You twist them, they become warm. You put them inside your gloves and keep your hands warm. And that's an exothermic reaction, one that releases heat. So endothermic reaction absorbs heat, exothermic reaction releases heat. Now let's go ahead and talk about some phase changes. Now let's begin with the name of a phase change. So when a solid turns into a liquid, that is melting, and a liquid turning back to a solid, that's called freezing. When the liquid evaporates, it turns into a gas, but when a gas turns back to liquid, we refer to that as condensation. And finally, if you go from a solid to a gas while skipping the liquid phase, so straight from solid to gas, you refer to that as sublimation. The opposite, where a gas turning into a liquid is referred to as deposition. So the change from one state to another without changing its chemical composition is just referred to as a physical phase change. All right, so there's no chemical changes here. It's just a phase change, just changing from one physical state to another. Now, going from a solid to a liquid to a gas, so from left to right on the slides, from solid to liquid to gas, that's an endothermic reaction. Energy needs to be supplied. Picture if you have a solid block of ice on the left, you would have to supply with energy to get that block of ice to melt. And once you have water, you would have to supply with more energy to get that water to go ahead and evaporate into a gas of vapor. All right, now the opposite is true, going from right to left, from the gas turning to a liquid, turning to a solid, that will be an exothermic reaction. That means that the gas will have to release its energy so it can condense from a gas to liquid, and the liquid have to release its energy so they can go from a liquid and freeze and turn into a solid. So the arrows represent the directions for an endothermic reaction versus an exothermic reaction. Now, quick distinction between what is a vapor versus what is a gas. At room temperature, roughly around 25 degrees Celsius or approximately 72 degrees Fahrenheit, so that's room temperature, a gas will stay in the same phase. For example, oxygen at that temperature will go ahead and stay as a gas. But in contrast, if you have a vapor and you cool it down to room temperature, that vapor is going to go ahead and condense and turn into a liquid. Often you see that on the picture on the right when you might have spent a little bit too much time in the shower and there's condensation in the room and you see it in the mirrors. And that is once the room begins to cool down, a lot of the vapor is going to condense into a liquid. Now let's talk about boiling point. Now the boiling point of water, if I were to ask you, what is the boiling point of water? Most people will be able to tell me, yeah, in Celsius is 100 degrees Celsius. Fahrenheit 212 Fahrenheit. But let's stick with Celsius, 100 degrees Celsius. Now you may notice that the pressure affects the boiling point. So if the pressure increases, the boiling point is going to go ahead and also increase. And if the pressure decreases, the boiling point will decrease. So the boiling point of water actually changes. We say is 100 Celsius, but that actually changes. In places such as Denver, where you're higher up in the mountains, there's less pressure. So the boiling point, when there's less pressure, the boiling point would also drop. So it's now somewhere around 96 degrees Celsius. All right, but if you're somewhere with high pressure, let's say, for example, Death Valley, which is below sea level, so it has high pressure, the boiling point elevates. Now, water doesn't boil at 100, it will boil at 101. So then again, if I ask you one more time, what's the boiling point of water? Is it 100? Not in Denver, not in Death Valley. All right, when we say 100, we refer to it as usually at sea level. And usually, more specifically, what we're talking about is at a particular pressure. At sea level, we understand that the pressure is 1 atm, 1 atmosphere. So in the slide, it says the normal boiling point. That's the one we're normally talking about. The normal boiling point is the temperature at which the vapor and pressure are equal to the standard atmospheric pressure of 1 atm. All right, now, so the boiling point could go up and down depending on the pressure, but when we say 100, we're immediately assuming that the pressure is 1 atm. The same is true for the melting point. If I ask you at what point does ice begin to melt, everyone would say in Fahrenheit, that's 32 Fahrenheit. In Celsius, that'll be 0 Celsius. All right, so does pressure affect that as well? And yes, it does. At higher pressure and lower pressures, that's also going to affect whether the boiling point or in this case, the melting point changes, either goes up or down. So when we say that the boiling point of water is 0, again, we're referencing that it's got to be at standard pressure 1 atm or at sea level. So if you change the pressure, that will also change its melting point. So when we say the melting point of water is 0, we're really referring to its normal melting point at a pressure of 1 atm. The normal melting point is the temperature which the vapor pressure of the solid and liquid phases are equal to each other. Again, that happens at a pressure of 1 atm. Now, condensation, let's go ahead and wrap up with that before doing some graphing. The condensation of a substance is normally called liquefaction. Now, that is a condensation of a substance that is normally a gas. In the picture, you see liquid nitrogen. Nitrogen is normally a gas. So could you turn it into a liquid? Sure, you could. What do you call the process to turn a gas into a liquid? It's called liquefaction. What do you do in liquefaction? Well, you need to increase the pressure quite a bit. So put in there high amounts of pressure plus lower the temperature. And if you increase the pressure while lowering the temperature, that will achieve liquefaction. Up next, we're going to go ahead and have a discussion on how to draw a phase diagram. In this slide, we're going to go ahead and discuss phase diagrams. A phase diagram is one that shows the relationship between pressure, temperature, and how it affects the physical state of a substance, whether it's a solid, a liquid, or a gas. So here we have solid, liquid, and gas. The solid section is right there in purple. The liquid is in the tan color and the gas is in the green color. All right, so now let's say I have a substance that is a solid, and I'm going to go ahead and put it here in the center. I'm going to put an X right there. All right, so we have a solid. Now, how can you turn a solid into a liquid? Most people would say, well, if you heat up a solid, it will melt. And that is correct. So I'm going to go ahead and increase the temperature. So let's say increase the temperature. So I'm going in that direction. Now I stop heating it at this point. You have taken it from a solid to a liquid. So yeah, to change the physical state of a substance, you can go ahead and heat it up. But what else could you do? If you go ahead and also lower the pressure, so in this case, we have our starting point right here, and we begin to lower the pressure. At this point right here, notice we're in the tan phase, and it will be turned into a liquid. All right, so a liquid you can turn a solid into a liquid by either changing the temperature or changing the pressure. All right, if we were to continue dropping the pressure, we can go by the liquid section and into the gas section. So we can go ahead and go from solid to liquid to gas in this diagram by just changing the pressure, even while keeping the temperature the same. You could also do the same by changing the temperature. Again, if we start from the solid and heat up the substance, it'll turn to liquid. And if we heat it up some more, you can turn it here into the green section and turn it into a gas. All right, so phase changes not only rely exclusively on temperature, but also pressure will affect whether you have a solid, liquid, or gas. All right, so that's very important to keep in mind. All right, up next, we're going to go ahead and talk about the triple point. All right, the triple point, you'll find it in diagram here on the bottom left corner. And the triple point is a point where the temperature and pressure are such so that all three physical states could exist and they are in equilibrium. All right, so that is a bit of a strange point because you could see ice cubes that are boiling, and it says that boiling ice cubes. Yeah, it looks very strange. So that is the triple point. All three, solid, liquid, and gas, exist in equilibrium. Next, the critical pressure. So find the critical point on the diagram. Here we go. And if you draw a line all the way to the left-hand side, whatever that is, that value would be its critical pressure, the pressure needed to liquefy a gas at its critical temperature. So you have this very, very hot gas and you want to liquefy it. What would you need? You would need the critical pressure to go ahead and liquefy it. All right, follow up that one with critical temperature. Again, we're going to look at the critical point here again. And there it is. And if we go straight down, here's the temperature. All right, now that temperature, once you go beyond it, you always have the substance be in the gas phase. So it says the highest temperature, which the vapor and gas phase can exist in equilibrium. After that, you always have a gas. All right, up next, we're going to go ahead and take some time to draw a phase diagram, and with including a triple point, melting point, boiling point, and critical point.
In example 1, we're asked to draw a phase diagram using the following data. So given to us are the triple point, melting point, boiling point, and critical point. Now for the boiling point and melting point, notice that they're at a pressure of 1 atm. So that means that the normal boiling point, normal melting point. So we're going to go ahead and put all the data into this x and y axis, where we're going to have the pressure on the y axis and the temperature in Kelvin on the x axis. So let's go ahead and get started. First of all, the triple point. The triple point is at 0.5 atm and 300 Kelvin. So for our pressure, it'll be 0.5 atm and 300 Kelvin. So we're roughly going to put it around this spot right here. Next, melting point at 1 atm and 150 Kelvin. So it'll be 1 atm, 150 Kelvin, somewhere around this spot right here. Now let's go ahead and label it for MP for melting point and TP for triple point. Next, for our boiling point, 1 atm and 500 Kelvin will be somewhere around this spot. And let's go ahead and label that BP for boiling point. And lastly, for a critical point, we're going to have it at 3 atm and 800 Kelvin. So it'll be 3 atm and 800 Kelvin, somewhere around up here. That's going to be our CP for critical point. All right, now that's enough information for us to go ahead and draw a phase diagram. I want to go ahead and start at the critical point and make my way through the triple point, through the boiling point, all the way down here. Now you do get some artistic liberty at exactly where it's going to go, but I'm going to go ahead and try to follow the trend that I see developing. So I'm going to begin here and just curving. And somewhere around there. Let's clean that up slightly. All right, so there's our line, not too bad. Now the next line is going to go from the triple point through the melting point and just continue a bit. All right, and there we have it. Now that's our phase diagram. I do take a little bit of liberty exactly where it's going to go as I go away from the melting point. So if your graph looks slightly different, that's okay. Now let's talk a little bit about this phase diagram. What does it tell us? It tells us when you have a solid, liquid, or gas. The phase diagram is referring to those three phases, solid, liquid, or gas. So this corner right here, that's actually our solid. I'm going to put an S for solid. Here, that's our liquid section. Let me go ahead and write liquid. And over here will be our gas section. All right, so there's our phase diagram with the data that was provided for us. In example 2, we're asked some more questions regarding this diagram. In example 2, they ask you, can you predict if you have a solid, liquid, or gas using the following data? So we're going to have for each one of those, we're going to have to make a prediction whether you have a solid, liquid, or gas. So the answers, I'm going to go ahead and put them on the board, put them up here, A, B, C, D, and E, referring to these A, B, C, D, E, and we'll figure out where they are exactly. All right, so I'm going to change colors a bit. Let's go with the blue, and the first one, A, is at 0.5 and 100 Kelvin. So here's 0.5 pressure, 100 Kelvin. So it'll be roughly around here. I'm going to put an A in its spot. Maybe I'll erase my solid. I'll rewrite it in a bit. But that one, it was in the solid section. I'm going to put here solid. 4B is 1.5 and 200 Kelvin. So 1.5 will be here and 200 Kelvin. This is where point B will be, and that is in the liquid section. Point C is a 1.5 and 300 Kelvin, so 1.5 slide it over. That's point C right there, still in the liquid phase. Point D is a 0.5 and 500 Kelvin, so here's 0.5. We're going to go all the way to 500 Kelvin. So there's point D at that spot right there, and that's in the gas phase. And finally, point E, it is a 1 atm 700 Kelvin. So here's 1 atm and 700 Kelvin is right around here. So point E is in this vicinity. So that is also in the gas phase. So the answer from A through E are solid, liquid, liquid, gas, gas. And that's where they are at on the phase diagram. All right, that takes care of example 2. Let's go ahead and take a look now at example 3. In this one, they ask you find the boiling point at the following pressures. All right, so the boiling point of a substance, let's say for water, we would say boiling point is at 100 degrees Celsius. But that boiling point can change depending on the atmospheric pressure. All right, so in places where there's lower pressure normally, such as Denver, you might have a different boiling point. Water might not boil at 100, it might boil somewhere between around 96 degrees Celsius. All right, in places where there's more pressure, like Death Valley in California, the boiling point of water is normally 101 degrees Celsius. So it does vary regarding the pressure. So when they ask you here, what is the pressure, what is the temperature at these pressures, it's going to go ahead and give us different values. I'm going to go ahead and write the answers here for A, B, and C, referring to these questions A, B, and C. So find the boiling point at 0.75 atm. I'm going to go ahead and use my green for that one. 0.75, so here's 0.5, there's 1, so 0.75 is right around here. What you want to go ahead and do is do a horizontal line going across. I'm going to go ahead and draw it across, trying to keep it as straight as possible. And when it hits this line, the boiling point between the liquid and the gas phase, that when you hit that line, that's where you go down. And I'm going to estimate it's a little bit past the 400, so I'm going to estimate somewhere around maybe 410 Kelvin. That would be the boiling point at 0.75 for the substance. The next one, 1.25. So here's 1, there's 1.5. So in the middle, again, we're going to do the same where we do a horizontal line. And when we hit this line right here, again, between the liquid and the gas, we're going to go ahead and go down and read the number that's right here. It's somewhere between 500 and 600 Kelvin. Slightly after it, we're going to go ahead and take a guess around maybe 560 Kelvin. Lastly, in part C, we get a pressure of 2.5 atm, so that will be over here. So we're going to go ahead and draw a horizontal line one more time. Where it hits the line, goes straight down. All right, and it's between 700 and 800, a little bit to the left of it, so let's go with 740 Kelvin approximately. All right, so those will be the boiling points at those different pressures. For our final example, example 4, they go ahead and they ask you now find the melting point. The melting point is between the solid section and the liquid section. So we're looking at this line here. All right, so we're going to go ahead and use red for this one. And then they ask us again, the same pressure, 0.75 for A. So I'm going to go ahead and put it over here. This will be for this problem that we're working on now. We'll put the answers there. So find the melting point at 0.75. So we'll go with this line. Same thing. And when we hit this line, rather than that one, because this is for the boiling point, that's for the melting point. When we hit this line, go straight down and read this number. It looks like to be right in between 100 and 200. So let's go with 150 Kelvin. Next on 1.25 ATM, this line again. And where it hits that line, we go straight down. Looks to be, again, in the middle between 0 and 100 Kelvin. So I'm going to go with 50 Kelvin. And the final one at 1 ATM. All right, so when it hits that, then it goes ahead and goes down. So that's going to be somewhere around 140 K. All right, so those will be our answers to the melting point at those particular pressures. All right, awesome. That takes care of example 4. This brings us to the end of the first lesson of Unit 6. Thank you so much for watching.